All right, so let's talk about this one. This one's on your homework 1649. The setup is we've got this bar. It's going to rotate. Um, I guess it's opening. It's opening up somehow. And it's attached to another bar, and then that's attached to a piston or something. And that piston in there is restricted to vertical movement. So it's in a channel or something like that. And what we're asked to do is to determine the velocity and acceleration of that piston um, based on a particular angular velocity omega. Okay, uh, this is a challenging problem. Okay, and so what I've done to walk you through this one is I've worked it all out on a piece of paper. I took a picture of that piece of paper, and then I'm going to walk you through the solution on the next slide. I think that's going to work pretty well. Let's see if it does. All righty. So let's just take a look at some of the geometry right now. So we have our angle theta right in there. And then I made up another angle, phi, like this, okay? And the reason for doing that is it enables us to create x and y coordinates based on the angles theta and phi. So x is given by this expression here, and y is given by this expression up here. So let's look at the x, okay? So it's L cosine theta, so that's coming across a certain amount, all right? And then L sine theta comes the rest of the way. So those two components together across the bottom of this thing here and here constitute x. Now, what the problem tells us, you can go back and look if you want to. What the problem tells us, though, is that that's equal to L. All right. So right off the bat, we get this sort of interesting relationship. Oops. Or 1 is equal to cosine theta plus sine phi. Okay. Now, that's only a quirk of this particular geometry, all right? I hope everybody understands that. That's not some brand new trig identity. It's just unique to this particular situation, okay? What it does allow us to do, though, is to figure out what phi is. And the problem asks for theta equal to 60 degrees, which then means that theta, if you run the math on equation A, is equal to 30 degrees. By the way, I'll try to put this document into eLearn for you so you can have a better copy of it maybe. All right. So let's keep on going down because remember, our whole process here is to set up the geometry and then take derivatives. So we've got geometry in the horizontal direction and geometry in the vertical direction. All right, so we've got our x and we've got our y, and we're going to have to take derivatives on both of those. So I've worked this problem many times, and it's super easy to go in a wrong direction, go in a direction that you end up banging your head against the wall. So this is one that just takes a lot of patience, and the best thing to do is just start with defining x and y, and then take your derivatives. So let's take our derivatives on x. The derivative of 1 is 0, and I'm moving on down to here. The derivative of the cosine theta becomes minus sine theta, theta dot. And the derivative of the sine phi becomes cosine phi, phi dot. All right, remember, theta and phi are both going to be a function of time. That reduces then to equation B, which is kind of handy. All right, another kind of interesting relationship. And equation B allows us to compare theta dot and phi dot. Now, theta dot is omega, so we can get phi as it pertains to omega. Now, if you plug in 60 degrees, if you plug in 30 degrees, then what we find is at that specific point, 60 and 30, you get that phi actually is omega. Phi dot is omega. Now, that only happens at 60 degrees and 30 degrees. If you use 59 degrees, find a new phi, it doesn't work. If you use 61 degrees, find a new phi, it doesn't work. But precisely at 60 and 30, then we get phi dot is omega. Now, that's probably because what we're dealing with at that point is a perfect isosceles, a perfect equilateral triangle. Okay, but anyway, so there's that relationship. Let's move on. Continuing with our horizontal information, we take the next derivative. The next derivative gets us down to this mess here. Oh, I want to use a different color. Gets us down to this mess here. All right. So let's take a look at that. We've got the term in equation B, we've got the term sine theta, theta dot. So we got to do each part one at a time. So the derivative of sine theta gets us cosine theta, theta dot. All that is times theta dot. Then we have to do the other part of sine theta, theta dot, which is we preserve the sine theta. We take the derivative of the theta dot, which gives us a theta double dot term. And we do something similar on the other side. Now, when we simplify that, we get a theta dot squared and a phi dot squared. I saved the phi double dot. I didn't save the theta double dot. Theta double dot is 0. And you might want to go back and take a look. The reason we know theta double dot is 0 is because it says a constant angular velocity. Okay, so we can toss theta double dot term. What follows then is some simplification, and we get a relationship down there. I need to move this thing. Get this relationship way down here. Okay, that's equation D. Because when we plug in 60 and 30 and 30, we end up finding out that phi double dot is some constant times omega squared. Okay. Now, in terms of units, that works out good. This should be an acceleration. It should be something per second squared. Here, we've got something per second quantity squared. So that works out well for us. So we get this relationship right here. All right. Now, if you don't know how something's going to turn out, I've talked about this before. You just head down a road and see what you get. You may find that there's information that can help you later. And that's the case here. Even though we seem to have hit something of a dead end, and we might be, well, why do we care about this? Well, remember, we've got a whole other half of the geometry to deal with, the vertical half up here, equation D. All right. Now, we'll take the derivative of this guy. All right. Sine theta becomes cosine theta, theta dot. Cosine phi becomes sine phi, phi dot. Don't forget the negatives there. And then we know that theta dot is omega. Phi dot right here, we can plug in from our relationship down here. They're both omega. And then it turns out we plug in all of our information, and y dot simplifies to this thing right here, which is that's pretty darn cool. Okay, just L times omega. There's one of our answers. We were looking for the velocity and the acceleration. There's the velocity of this little piston piece in here going up and down. Okay. To get the acceleration, we got to do the whole thing over again. So we take the derivative, all right, and again, cosine theta turns into sine theta, theta dot. We preserve the theta dot. Sine phi becomes, and then we got to do the other part, cosine theta double dot, this right here. Then sine phi becomes cosine phi, phi dot, with our phi dot from the outside. And then finally, sine phi double dot right here. Okay. Again, we're going to toss the theta double dot term. It doesn't matter because it's 0. And that gets us to this equation right here. Now, what I did was right here, phi double dot, I chose to substitute in from down here. All right, right there. So cosine theta sine phi in this case is 1. Remember, I had that up here anyway. So I've got 1 over cosine phi. So that gives me this term here. I plug that in for my phi double dot to get this relationship right here. Sine over cosine gives me a tangent. Then I plug in my values, boom, 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 and I get this guy, 0.577 L omega squared. There's our acceleration, okay? I seldom look at the solutions. It's a point of pride. But I did verify this one with the published solutions, and both those answers are correct. So super messy, but it's there. Things that I want you to really latch onto are things like when we go from something like this, cosine theta, theta dot, once we take that derivative, okay, we're always going to get 2 terms out of that. All right. And 9 times out of 10, you're going to end up with a theta dot squared, which is omega squared when you do that. Okay. So things get more and more messy. And then we just plug in our numbers and we're okay. Okay. I will put a copy of this into eLearn so that you can have a better copy to look at than just trying to watch this on a video. And then maybe if you have this worked out and you can kind of go through it, watch the video again, kind of go through it piece at a time. It should work out pretty well for you, I hope.